all your accomplishments and everything that you've done for reproductive medicine for many years.
Thank you. Can you see the slides?
Yes, we can see them.
Can you see me moving them?
Yes.
Okay. All right. So whenever you're ready, we can get started.
We are ready for you, Dr. Adachi. Thank you so much.
Thank you, Ricardo. Okay. Well, it's been a technical tour de force to get to this point, but let's hope that it works. By way of a reminder, although I'm sure all of you are very cognizant of the dates, in 2028, so in 3 years from now, we will be celebrating the 50th anniversary of in vitro fertilization, which started, as you know, in the UK. The very first report of successful IVF was published as a letter to the editor at The Lancet, which is shown here. And of course, in the United States, received major exposure by displaying Louise Joy Brown on the pages of Time magazine. The main protagonist here, as you know, was Robert Edwards, PhD, who received the Nobel Prize for the IVF accomplishment in 2010. You may ask, why didn't two of his key collaborators, Dr. Steptoe and Jean Purdy, why did they not share in the Nobel Prize? And the reason, unfortunately, is prosaic, and that is both Dr. Steptoe and Jean Purdy passed away before 2010. And it is the policy of the Nobel Prize Committee to award the prize only to living recipients. And only Professor Edwards at the time was alive to receive the award. As a matter of fact, he was quite unwell, and it was his wife who ended up going to Stockholm to receive the Nobel Prize. Dr. Edwards himself passed away in 2013, aged 87, having made clearly a very significant contribution to reproductive medicine. The United States was in this case not the leader, but rather the follower. And the theme that made IVF possible in the United States was ultimately assembled in Norfolk, Virginia. It included, among others, Drs. Howard and Georgiana Jones, who left Johns Hopkins at that time due to retirement. And the team you see here was really the team that enabled IVF in the United States. The first IVF birth in the United States transpired on December 28, 1981. And that, of course, was Elizabeth Jordan Carr, who was the first American IVF baby, who is shown here on the pages of the Boston Globe and Life magazine, to mention a few. That was a major breakthrough. But today, we will be speaking about the next breakthrough, although its implementation is unlikely to occur tomorrow. Going forward, as I just alluded to, we will be speaking about in vitro gametogenesis, the notion of making eggs and sperms in vitro from essentially any source, courtesy of stem cell technology. And I will, of course, elaborate to clarify what I just said. But before we do, we might want to take a step back and recall the seminal contribution of Aldous Huxley in 1932 in the form of A Brave New World, in which many of the reproductive technologies we use today were predicted, envisioned, and described in some detail. At the time, Professor Huxley predicted that eggs will be produced via ex vivo ovarian cultures, that embryos will be created via in vitro fertilization, and that newborns will arrive via ex vivo ectogenesis. Well, the first prediction is what we will be describing today. The second prediction is, of course, widely applied in the US and elsewhere. The notion of newborns being gestated and delivered through ectogenesis is yet a dream, and it may or may not materialize at any point in the future. But embryos via in vitro fertilization is, of course, routine today. What we are going to try and discuss is what might be coming next. You may recall that in chapter 1 of Brave New World, the director of hatcheries and conditioning, so-called, said, one egg, one embryo, one adult, normality, making 96 human beings grow where only one grew before, progress. And as you will see, in vitro gametogenesis, having 96 human beings or the precursors thereof grow in 96 well cultures is quite routine. The beginning was modest, but is entirely, and may still be entirely, traceable to Japan. Somewhere around 2013 or thereof, I became aware of the work of Dr. Saito and Hayashi, who at the time were working together at Kyoto University. Having gone to Japan for some other reason, I booked a flight to Kyoto, and I visited the two gentlemen and spent a whole morning talking to them and learning for the first time firsthand what in vitro gametogenesis was all about. Since that time, Professor Saito remains in Kyoto University and continues to develop in vitro gametogenesis, mostly in the human now. Professor Hayashi moved to Kyushu University and has developed other technologies, although he continues to have an interest in vitro gametogenesis. All of this, of course, is entirely attributable to pluripotent stem cells, which come, as you know, in two varieties. They are so-called embryonic stem cells, and they are induced stem cells, and I'll explain the difference. You can essentially use stem cells to make any cell lineage. You can make motoneurons, you can make retinal neurons that could be applied in the retina, and you could use dopaminergic neurons, apply them to the striatum of patients with Parkinson's disease, for example. Here are a few examples. A Nature paper from this year reports on a paralyzed man who stands again after receiving reprogrammed stem cells. In other words, engineered stem cells were injected into the spinal column of this individual, who now walks again. Similarly, also in Nature Aging in this case, a report on stem cell therapies for Parkinson's disease. Same idea. Stem cells being introduced into the substantia nigra and some recovery of certain facets of Parkinson's disease. But today, of course, we will focus on gametes and the idea that we can produce gametes from stem cells essentially in unlimited amounts and in vitro. Science magazine appreciated this development and dedicated a full spread to it in 2021, authored by the two Japanese individuals I just introduced. The New England Journal of Medicine, not to be outdone, commissioned a paper from Mary Herbert and Azim Surani, who wrote a paper titled Oocytes from Stem Cells. And in 2023, I had the pleasure and privilege of organizing a workshop at the National Academy of Medicine, which dealt with in vitro derived human gametes as a reproductive technology, which is the topic, of course, we are discussing today. The Nuffield Council on Bioethics, which, as you know, is the most prominent British bioethical organization, has also placed in vitro derived gametes at the top of its human reproduction agenda. As you can see, in vitro derived gametes are at the very top of the list. Yes, the Nuffield Council was going to study this and more. But ultimately, at the top of the list was in vitro gametogenesis, which we can all agree is a disruptive technology that may be achievable in a human, and we will talk about that, and at what timeline, which we will also attempt to define. But as I indicated already, none of this would be possible without the generation of pluripotent stem cells, which are the precursors of the gametes we are talking about. The first technology to produce stem cells was known as somatic cell nuclear transfer and dates back to 1958. This technology, somatic cell nuclear transfer, was developed by John Garden, then at Cambridge University, who published in Nature. The technology was relatively simple. He started with a somatic nucleus, inserted it into a nucleus-free oocyte, and created a quasi-zygote, which developed into a blastocyst, gave an inner cell mass, from which embryonic stem cells were derived. Many years later, in 2006, the induction technology was introduced, and it primarily dominates the day now. It was the creation of Shinya Yamanaka from Kyoto University, who on the pages of Cell reported starting with a somatic cell, transfecting it with select transcription factors, and producing what we now call induced pluripotent stem cells. Both individuals were awarded the Nobel Prize in Physiology and Medicine in 2012. And so when we now focus on in vitro gametogenesis, we need to keep in mind that the starting material is a somatic cell that we convert by one of these technologies to either an embryonic or induced pluripotent stem cell. And from there, we go to a gamete. Now, what do we need to know, or what are the prerequisites for this to ever happen? Well, you need to know the so-called germ cell specification pathway. What cues have to be applied? By what sequence? By what timing? And in the context of a niche. A niche is really the environment of the germ cell. And I don't have to tell this audience that oocytes are surrounded by granulosa cells and theca cells, and that sperm are surrounded by Sertoli cells. And so there's always a niche or a surrounding somatic cell component within which the germ cell develops. The beginning was very modest, but can probably be traced to a science paper in 2003, the senior author of which was Hans Scholler, who was then a postdoc at the University of Pennsylvania. He later became the director of the Max Planck Institute for Molecular Biomedicine in Germany. That same year, Toshiaki Noche from Japan published on the proceedings of in the Proceedings of the National Academy of Science a paper titled Embryonic Stem Cells Can Form Germ Cells in Vitro. George Daly, who is now the Dean of Harvard Medical School, published in Nature a paper titled Derivation of Embryonic Germ Cells and Male Gametes from Embryonic Stem Cells. And René Rehopera, who at the time was at UCSF, published a comparably informative paper. In the next 10 to 15 years, several significant papers saw press in Nature, in Science, and in Cell, and again between 2010 and 2015, more of the same. So by 2015 or so, the state of the art was that the germ cell specification pathway, we realized, is not conserved between the rodent and the human. In other words, we needed to know the book of instructions for the human if we were going to produce germ cells in vitro. Moreover, the genetic networks involved proved to be quite distinct between the rodent and the human, which made the task even more complicated. In a word, when we look back at 2015, we can say that we understood that stem cells could be converted to primordial germ cell-like cells, but we really didn't know how to take those cells and convert them into haploid post-meiotic mature gametes. In a word, we mastered the extragonadal component of the process, but we yet had to master the intragonadal component thereof. The final frontier was what we're looking for, that is in vitro gametogenesis all the way, producing eggs and sperm entirely in vitro. The first demonstration of such on the female side was contributed by Professor Hayashi, to whom I introduced you earlier. In a Nature paper published in 2016, just about the time the American Society of Reproductive Medicine met in Salt Lake City, Professor Hayashi reported this graph, wherein embryonic stem cells were converted to primordial germ cell-like cells, combined with gonadal somatic cells, and gave rise to primary oocytes, eventually M2 oocytes, that are shown on the left-hand slide. And those in turn gave rise to fertilized egg, to blastocysts, and to pups. In a word, he took embryonic stem cells or induced pluripotent stem cells all the way from the beginning to living pups. More of the same happened in the male, this time courtesy of Michinori Saito. Here again, there was an in vitro reconstitution of the whole male germ cell development from mouse pluripotent stem cells. And so, at least in a rodent, we now know how to take an embryonic stem cell or an induced pluripotent stem cell and make a gamete out of it. But the human paradigm is still lagging. Professor Saito took a stab at this in 2018 in a science paper. He was able to start with human primordial germ cell-like cells, combine them with xenogenic ovarian cells, and took the primordial germ cell-like cells all the way to the ogonial stage, which is quite advanced. However, he never got as far as the M2 oocyte stage, which is what it would take to fertilize and proceed from there. And so at this point, we're not quite there yet, but we recognize the scientific and translational promise of in vitro gametogenesis. On the side of advancement of science, we now are on the precipice of having an inexhaustible supply of germ cells. We may be able to produce so-called functional null-mutant analysis, which scientists are very keen to see, basically knock out one gene at a time and ask, what does that do? We could also proceed to study germ-somatic cell interactions in ways we couldn't do before. Clinically speaking, we might be on the precipice of reversing germ cell failure. We could, in principle, replace gametes, autologous gametes that would be produced, let's say, from a skin cell. And we could gene edit those gametes if there was a genetic defect to begin with. And in theory, although that will be a subject of a separate talk, one could then proceed to envision what we call same-sex parenthood. That is to say, a child that is at least genetically the child of either two men or two women, although the resulting gestation needs to be, of course, undertaken by a woman. IVG is likely to affect IVF when and if it becomes practical. For example, it could eliminate the need in stimulation and egg retrieval. As you know, women who undergo IVF must receive gonadotropin injections to stimulate egg production, and those eggs have to eventually be retrieved, albeit by a minor surgical procedure. All of that could be potentially passed over. We could potentially do away with so-called gamete donation, which is, of course, age-dependent, because we could produce gametes. We no longer may need the so-called donor banks. And we could convert IVF effectively to a laboratory procedure because the women in question will not have to be injected with drugs, nor will their oocytes need to be retrieved by surgical technology. We still will require endometrial preparation and transfer, and possibly although not suddenly, we could improve affordability and therefore access. All of us know full well that IVF tends to be expensive. Insurance coverage tends to be variable. In theory, IVG could be a more practical, affordable solution. I say so with some trepidation because, having observed the American genius to jack up prices, I suspect that IVG may fall into the same category in the final analysis. Now, none of this can occur in a vacuum, and definitely significant regulation will have to be applied before this is ever deployed in the context of a human being. This is the natural FDA jurisdiction. And in the FDA, the so-called Center for Biologics Evaluation and Research, or CBER for short, is likely to be the unit concerned with the approval of in vitro gametogenesis. In their lingo, in vitro gametes will come under the heading of so-called HCT/Ps, or human cells, tissues, and products. But it is the FDA that ultimately will have to give IVG the approval to be applied in the context of the human. Now, as we speak, there are some nascent, I would say, commercial US efforts in this arena. I will limit myself to one. This is a product known as Gamito, which is produced by a company called Fertilo. And as the title suggests, the company was given FDA clearance for the first phase 3 clinical trials of induced pluripotent stem cell-based therapy. This is IVG in its, shall we say, practical application that is now being dealt with by a company that is based in New York State. In their advertising material, Fertilo speaks about making IVF and egg freezing shorter, safer, and more effective. They propose to mature eggs outside the body, which could reduce the need for hormonal injections, improving the patient experience and safety while maintaining efficacy. And they suggest that 12 days of stimulation could be reduced to 3 days of the same. Fertilo Cycles requires 2 to 3 days of in vivo gonadotropic stimulation, thereby reducing the gonadotropic requirement by circa 80%. Fertilo's ovarian support cells seem to take the in vitro maturation of retrieved immature eggs. And Fertilo is now, as we already saw, in phase 3 clinical trial. So for now, I would say stay tuned. It's an evolving story, but it's the latest frontier in reproductive medicine, which we need to pay attention to because it's moving fast. And at some point, definitely the younger member of the audience who may end up in reproductive endocrinology and infertility may need to be fully aware of this technology and, more importantly, be familiar with its application. So with that, I'm going to close this morning's discussion, and to the extent that time permits, I will be pleased to entertain any questions I know the answer to. So thank you very much.
Thank you very much, Dr. Adachi, for this very exciting presentation. We have our faculty and our residents here in the room, so does anybody have any questions for Dr. Adachi? Now, Dr. Adachi, this last technology that you presented,
Yes.
it's obviously clearly not in vitro gametogenesis, but really getting the last stages of oocyte maturation to turn into a haploid cell.
Yeah.
And of course, we have to start somewhere. So do you foresee that this is going to be clinically available within 3 to 5 years as an option?
I think we need to give ourselves more time, Ricardo. Obviously, none of us are in the business of predicting, and we can't be too accurate. But I think we are barely at the beginning of this story. It's a nascent story. The biopharmaceutical industry is just getting started on making this happen. And without them, of course, we cannot assume widespread application. So obviously, I don't know how long it will take, but I would be very surprised if we were in a new mode of practice 10 years from now, for example. I could be wrong. I could be definitely proven wrong by reality. But at this point, none of us really have firm ground upon which to predict how long this would take to industry to catch up, to the regulatory agencies to approve, and for the clinical enterprise to embrace the new technology and apply it.
The other piece of this technology that we did not talk about today was the growth of an embryo outside of the uterus. And it's interesting that I was in Valencia, Spain this year at the Carlos Simon Foundation, and they've been able to take uteri from a hysterectomy patient and grow embryos in vivo or in vitro, if you want to put it that way, in this uteri that was connected to a oxygen supply, and grow embryos all the way past implantation to a positive heartbeat. So although it's not exactly what Mr. Huxley envisioned, there are some attempts already being made to try to grow embryos outside of the uterus already. Although it's in its very early stages, they've been able to grow these embryos to a significant degree outside of the uterus, although technically still a uterus that they utilize from a hysterectomy patient. But this may be the early stages of what would turn out many, many decades later into what Mr. Huxley talked about in his book.
No question about it. And the notion of incubating, if you will, embryos in a uterus, but in an extrauterine environment, or extra bodily environment.
Yeah, we're going to need to develop new terminology, Dr. Adachi,
right.
to describe this.
I have looked at that technology for a long time, and I have a fat package of papers that were sitting on my desk for the longest of time. But this technology clearly lags behind in vitro gametogenesis, and I'm not entirely sure we'll be able to make it real or make it happen. In other words, free up women, if you will, of the responsibility to carry gestation and eventually deliver it. I, at this point, remain to be convinced that this is feasible or even desirable, but I think we're way too early to say anything beyond what you and I already said, which is a vision of the future, but hardly a practical reality that is anywhere near application.
I mean, in today's world, we can already grow human kidneys in pigs by modifying their genetic makeup.
Mm-hmm.
You know, could it be that we modify uteri from, again, animals to be able to grow humans inside? And it may sound like a funny statement, but it may be a shorter route to reaching that level of technology relative to just growing humans completely outside of the body. And that may be the technology that would get developed. And it may sound like a crazy statement, but crazier statements have been done before. And a crazy book that was published a long time ago, 70 years ago, is turning out to become reality 70 years later.
Yeah, no, humanity, or the ingenuity of humanity, has come up with incredible developments. I mean, even IVF. If I were to ask you or other colleagues back in 1978 or 77 whether that's a possibility, I think we would have been hard pressed to say so. But human ingenuity, such that it is clearly coming up with more inventions than we could have anticipated. IVF was a huge breakthrough conceptually. IVG is likely to be just as impressive a conceptual breakthrough. And whether or not ectogenesis, if you will become a reality, only time will tell. But clearly, human ingenuity has taken what nature designed for reproduction, turned it on its head, and gave us what are now very distinct options that presumably are serving humanity well. So what the future holds, who knows? But I would not rule out any of the options you have speculated on.
Any other questions or comments from the audience? It seems like we have a pretty shy audience today, Dr. Adachi.
I met your audience many years ago when
yes.
I came there in person.
Yes. Well, Dr. Adachi, thank you so much for your time. This was an illuminating presentation, and we very much appreciate your time, your willingness to come back to us here in Springfield, even if it's virtually, and we hope that we can see you sometime again soon. Thank you so much for your time.
My pleasure.
I don't know if you can hear the clapping, but there's some clapping going on.
Thank you very much. I could hear it. Thank you.
Thank you. Bye-bye, and have a good morning.
Thank you.